The next part on the wave on the string section is the superposition of the two traveling waves. So let's consider here, if we have the two waves on the same string, okay, if we have the two waves on the same string, so now we just want to find the combined wave from these two individual waves. So what would we do? So that's one principle which is quite important that you should know. It's called the principle of superposition, which is saying that when the two or the more waves cross at a point, the displacement at that point is equal to the sum of the displacement of the individual waves. Okay, so let's consider this graph, right? This plot. So I have the two waves, okay, the first one and the second one, right? The first one is moving to the right hand side with the speed equal to the 1 meter per second, and the right one, right, also moving to the right hand side with the speed equal to the left hand side with the speed equal to the 1 meter per second as well. So now let's say that for each block here, right, it's going to have the length equal to the 1 meter. Okay, so this is at the times equal to the 0, but now when the times equal to the 4 seconds, it means that this wave, right, will move to the right hand side with distance equal to the 4 meter, because we say that the speed equal to the 1 meter per second. So it means that in the 4 seconds it will move to the right hand side with the distance equal to the 4 meter. The same for this one, right? It's going to move to the left hand side 4 meter as well. Okay, so let's draw the first one. Okay, so 1, 2, 3 and the 4 meter in this case. Actually I should move this. Okay, 1, 2, 3 and the 4. Okay, how about here, right? It's going to move to the left hand side with 4 meter. 1, 2, 3 and 4. Okay, so that's how it looks. Okay, so then we just want to combine these two waves, right? We just want to combine these two waves together. Okay, so let's say at the first part here, right, both displacement just equal to the 0. So then finally just equal to the 0. Okay, so now for this part, okay, for this part, the displacement of the first wave is the 3 blocks, and this one 0 block, right? So it's gonna go to be something like this one. Okay, for now this part, the displacement of this one, right, is the 3 blocks in the which is positive, right? But this one is 2 block negative. So it means that we have the 3 blocks and then minus the 2 blocks is going to be equal to 1 block here. Okay, and then for this, okay, for this part, it just the 2 blocks negative, so it just look like this, and then finally just 0. Okay. So that's how it looks. Okay, then with the terms equal to the 6 seconds, okay, so let's compare from t equal to 0. It means that this block will move to the right hand side with the 6 meter. 1, 2, 3, 4, 5 and 6. Okay, and now for this one, right, we move to the left. 1, 2, 3, 4, 5 and 6 as well. Okay, and data should be something like this, 0. Okay, so let's draw again, right? This come to this one, and now for this part, right, we have only the two blocks down, so it's just like this. Okay, and for this part, right, so we have the 3 blocks up and the 2 blocks down, so then we need to subtract to each other, right? So it's going to be the oops, it's going to be the one block up, and then finally it's going to be equal to the 0. Okay, now for the x second, right? Okay, again, so let's do this. So this one move to the right for the x blocks. 1 2 3 4 5 6 7 8. Okay, and this one move to the left, right? 1 2 3, sorry, where's it? One more time. 1 2 3 4 5 6 7 and 8. Yep. Okay, so let's see. It's gonna look something like this. Okay, so now you can see that if we follow this this term, right, you can see that this one, right, we move to the right hand side, and this one we move to the left hand side. So then at this time, both of them will be overlap to each other. Okay, so we can use the principle of the superposition, right, to find the resultant wave. Okay, so don't forget that the displacement at a point, right, is equal to the sum of the displacement of the individual wave, the one that we just, we have done already. And then after that, both wave, right, is gonna separate to each other, and it just travel to its own direction like this. So this one will move to this direction and to something like this. Okay. Okay, so then how about in the general case, if we want to combine the two sinusoidal waves on the same string, okay, at a fixed position x. Okay, so now for the simplicity, I just want to make the x equal to the 0, so that's why we don't need to write too much. Okay, so let's say that the first one, right, the first wave, we're gonna have the wave function, right, the y1, right, at the x equal to the 0, and then for the times t equal to the a1 times the sine of the omega 1 times the t. So it means that the amplitude of the first one is equal to the a1 and the angular frequency equal to the omega 1. So now for the second wave, I have the y2, right, the same at the x equal to 0, and then for the times t, I'm going to have the amplitude equal to the a2 and the sine function, right? So we have the omega 2 here as the angular frequency, and then plus the phi. So the phi here is going to be the initial phase difference between the wave y1 and the wave y2, right? So then again, we just want to find the resultant wave at the x equal to the 0. So then from the principle of the superposition, right, it said that, okay, the displacement at that point, okay, so for the x equal to 0 in this case, is equal to the sum of the displacement of the individual waves. Then in this case, it means that if I just want to find the resultant wave at the x equal to the 0 for the times t, right, so I can just sum displacement of the both waves. So it's just equal to the y1 and then plus the y2. But now, okay, just plug in the y1 and the y2 into this equation, right? So this is what I get, okay, equal to this. Then my question is, is it possible to write down this summation into this form, the new form of the wave? Okay, for example, the A here is going to be the amplitude of the new wave. The omega palm is going to be the new angular frequency of the new wave, right? And the phi palm, right, is going to be the phase, the initial phase of the new wave. Okay, is it possible? Actually, the answer is yes. Okay, it's possible to write down this summation into this form, but then we need to consider in the special case. Okay, we need to consider for the special case here. For example, let's consider this one. So let's assume that, okay, for the first case, let's assume that if the omega 1 and the omega 2 are the same. So it means that both waves will have the same angular frequency, okay? So we just make the omega 1 equal to the omega 2, and then also equal to the omega t, equal to the omega. Okay, then for the first case, let's just make the phi equal to the 0. Okay, so let me just write down here. So let's look at this equation, right? We're gonna have the y equal to the a1, okay, and then times the psi of the omega t, and then plus the a2, and then also times the psi of the omega t as well, because the phi is just equal to the 0. Okay, then here we have that the a1 plus the a2, right, because we have the same psi function here. Okay, a1 plus a2, and then times the psi of the omega t. So it means that, I mean, for the distant wave, right, so this one is gonna represent the amplitude. Okay, the amplitude of the resultant waves increases. Okay, so that's what we get. The amplitude of the resultant waves increases. Now, okay, so let's consider this picture. Let's say that initially if I have the wave, so let's say the A1, okay, so let's make the A1 to be the red one, the A1 here, okay, and then I have the A2, right, the amplitude of the second wave, the A2 here to be the A2. Okay, so now we just want to combine this wave together. Okay, so then finally we're gonna have the total amplitude equal to the A1 plus the A2, right? So the A2 is 1 block and the A1 is about 2 blocks. Okay, so it means that the A1 plus the A2 must be equal to about 3 blocks, right? So it's gonna go something like this. Nope. Kind of. No, wait. I should say. Yeah, so just write something like this, okay? And let me just. Actually, it should down a little bit. Yeah. Yeah, something like this. Okay, so the amplitude of this one equal to the A1 plus the A2. But don't forget that the angular frequency must still be the same, right? Because both of them, they have the same angular frequency here. Okay, another case, so let's say that the phi equal to the pi, right? So in this case, if the phi equal to the pi, then we're gonna have that the y equal to the A1 times the psi of the omega t, right? And then plus the A2 times the psi of the omega t, and then plus pi. Okay, so what is the psi omega t plus the pi? Which one is equal to negative of the psi of the omega t? okay, right? Then in this case, you can see that we have, okay, we have the same sine omega t, but this one we have the a1, this one we have the negative, the a2, right? If we combine together, we're gonna get the a1 minus the a2, and then times the sine of the omega t. So it means that the amplitude of the resultant wave, right, is going to be smaller. Okay, it's going to be smaller. So then the wave will just look like here. Look like this one. Okay, so that's going to be the resultant wave. Actually, let me just make it border. Yep. Okay. So again, right, this amplitude for this amplitude is going to be equal to the a1 and then minus the a2. Okay, so now in the general case, okay, if we have the angle phi, okay, in the general case, if we have the angle phi here, okay, so let's just write down. We say that the y, right, is going to be equal to the a1 times the sine of the omega t, and then plus the a2, and then some times the sine of the omega t, and then plus the phi. Okay, so then my question is, in this case, right, is it possible to write down as the a times the sine of the, maybe the omega t, and then plus maybe the theta, right? Is it possible to write down this summation into this form? Actually, it should just say to be the phi palm. Okay, is it possible to write down this summation into this form? Okay, I'm going to make you think first. You can say that, okay, maybe you can say that if we just separate this one, right? You can say that the sine omega t plus the phi is just equal to the sine omega t cosine phi, and then plus the sine phi times cosine omega t, right? And then, okay, if we have this as this, it just look quite messy, right? So I think it's impossible to write down, this summation into this form. Okay, so it means that in this case we need to find a new way, okay, to write down this summation into this form. But how? Okay, but how? We are going to use this. It's called the phasor diagram. Okay, it's called the phasor diagram. The phasor diagram is going to be a technique. Okay, it's going to be the technique that we can use to write down this summation, okay, of the same angular frequency but different phase and different amplitudes, right, into this type of the forms. Okay, so let's see. Okay, so we have the 3 steps that we need to follow. The first one is, okay, we're gonna write, the idea is to write the wave function y of an individual wave, right? So by the individual wave, it just means that this one and this one, okay, as a vector. Okay, so we're gonna write down the wave function as the vector such that the amplitude of the wave, right, will represent the magnitude of the vector, okay, the amplitude of the wave. So it's just this one. It's going to be the magnitude of the vector. and then the argument of the cosine function. Okay, so this argument, right, this one and this one, it's going to be direction of the vector to the positive horizontal axis in the counterclockwise. Okay, so that's going to be the conventional definition. Okay, so now for the step 2, right, you're going to find the resultant vector. So it means that we need to sum these two as the vector. And then finally for the step 3, right, the resultant wave function is the projection of the resultant vector on a horizontal axis. Okay. Okay, so we're going to try to understand the phasor diagram from these examples. Okay, so let's consider this example and then we can understand what the meaning of the phasor diagram. Okay, then okay, the two sinusoidal waves are traveling on the same string. Okay, so their wave functions are given by this. So the first one, we have the amplitude equal to the 1.5 meter, and we have the sine function which is the kx minus the omega t, right? The second one here, right, we have the amplitude equal to the 1 meter, and the argument is the kx minus omega t, and we have the phase difference between these two equal to the pi over 3, which is equal to the 60 degree, right? So now use the phasor diagram and write the resultant wave function in this form. Okay, in this form. So then how about if we just start by writing the axis first? Okay, but let's just start by writing the y1. One thing, let's notice this. Because because the both of them, right, we have the same terms, kx minus the omega t. Okay, and the phase difference between the y1 and the y2 equal to the pi over 3. Okay, so now to make it simply, I'm going to make the kx minus omega t equal to the 0 first. And then later on, if we get the resultant vector, I'm going to put the kx minus omega t back to its function. Okay, so I mean, the first of all, I'm going to make the kx minus the omega t equal to the 0 first. So then let's make the kx minus the omega t equal to the 0. Okay, so now this function, okay, we have the y1 equal to the 1.5 meter, and then times the psi 0, right, times the psi 0. So in this case, let's say that actually, let me think first. No, okay, I think it's, let me do it this way. Okay, so just leave the kx minus omega t first. So it means that, okay, to write out the vector y1, right, it's gonna point to this direction. Let's assume that it's just pointing to this direction. So this is gonna be vector y1. And then the magnitude of the vector y1 is just equal to the 1.5 meter. Sorry. The 1.5 meter. Okay, and then this angle equal to the kx minus omega t. So this angle equal to the kx minus omega t, because we say that the argument of the sine cosine function, right, is to be the phase of the vector. Okay, so now for the y2, okay, the length equal to the 1 meter, so the y2 should go to something like this. This means the y2, and the length equal to the 1.0 meter, right? And then the phase, right, equal to the kx minus omega t, and then plus the pi over 3. So we have the kx minus omega t here already. Then means that the pi over t should be this one. Okay, so this should be the pi over 3. So don't forget that when we're talking about this direction, right, we're going to make to the positive horizontal axis in the counterclockwise direction. Okay, so this is this part, but now we just want to write down the wave function as the vector. Okay, how? Let me just start from the y1. Okay, the y1 is equal to the 1.5 meters, okay, and then times the cosine of the kx minus the omega t I, because it's just pointing to this direction, and then plus the sine of the kx minus omega t j. Okay, now for the y2, we just do the same thing. We just write down the y2 in the form of the vector. So the amplitude is equal to the 1.0 meter, which is going to be the magnitude of the vector as well. And then times the cosine of the kx minus the omega t, and then plus the pi over 3 times the vector I, and then plus the sine of the kx minus the omega times the t, plus the pi over 3 times the vector j, right? Okay, so now we're going to make, everything to be simplified. Okay, so I'm going to make, as I just mentioned before, I'm going to make the kx minus the omega t equal to the 0. Okay, I'm going to make this way, the kx minus omega t equal to the 0. So then in this case, we can get that the y1, right, it's just equal to the 1.5 meter, and then times the cosine. Okay, so we have the cosine 0 equal to 1, right, equal to 1, and then sine 0 equal to 0. So we're gonna have only unit vector I here. Okay, so that's for the y1. Now for the y2. Okay, so we have the 1.0 meter, and then we have the cosine of the pi over 3 times the vector I, and then plus the sine of the pi over 3 times the vector j. Okay, now we just want to find the y. Okay, then we can get that the y, the resultant vector, right, is gonna be equal to the y1 and then plus the y2. Okay, so let's sum everything together. Okay, so I to the I and j to the j, right? So let's sum for the I first. So now for this I, we have the 1.5, okay, and then plus the 1.0 times the cosine of the pi over 3 times the vector I, and then plus, okay, so now for the j, right, we have only this component, which is the 1.0, and then times the sine of the pi over 3 times the vector j. So then Okay, so then cosine of the 60-degree, right, equal to the 0.5. So here we have the 2.0 times the I, okay, and then plus, so this is the sine of the 60 square root 3 over 2, right? It's just equal to the 0.87 times the j in the unit meter. Okay, so this one is going to be the resultant vector. Now for next step, we need to convert, okay, this resultant vector to be the resultant wave function. So don't forget that the magnitude of the vector, right, is just the amplitude of the wave, and the direction of the vector is going to be the argument of the function. Okay, then finally we can get the amplitude of the resultant wave function, right? Okay, so now this A is equal to the square root of the 2.0 square and then plus 0.87 square and square root, okay, which is equal to the 2.2 meter. So that's going to be the amplitude. Okay, so now we're going to find the phase phi, right, the initial phase phi. Okay, so let's look at the y first, right? We have the 2i and then 0.87j. So if we draw the triangle, oops. Okay, so this one equal to the 2.0 times unit vector I, and then plus the 0.87j. So it means that the resultant wave will just point to this direction. Okay, so it means that this angle, it must be equal to the phi. Okay, then we can get that the phi here is equal to the arctan of what, of the 0.87, okay, and then over the 2.0, which is equal to the 24 degree. Okay, so now for the conclusion, okay, so now for the conclusion, we can say that the y, right, which is depending on the x and the t, is equal to the amplitude. Okay, so we have the 2.2 meter and then times the sine of, okay, so now we need to put the kx minus omega t back, right? The sine of the kx minus omega t, and then plus the phi for the initial phase, the 24 degree. So this is the results. Okay, so now let's consider another case. Okay, because so far, right, we're just talking about when the omega 1 equal to the omega 2 and then equal to the omega. But now in this case, okay, so let's consider that the omega 1 is not equal to the omega 2, but we're gonna make the amplitude, both of them equal to each other, so equal to the A, and let's just make that the initial phase, right, it's just equal to 0. Okay, now equations. Okay, so we say that the y, right, equal to the y1 and then plus the y2. So previously we have this. Okay, so in this case it's going to be equal to the amplitude A, right, because we said that the amplitude must be the same and equal to A. Amplitude A, and then times the sine of the omega 1 times the t, and then plus the amplitude A, right? Because the A2 equal to the A as well. And then also times the psi of the omega 2 times the phi. So don't forget that the phi here equal to the 0. Okay, so now we need to combine these two waves. Okay, we need to combine these two waves, and let's see what happened. So then to combine these two waves, I'm going to use the trigonometry identity. It said that the psi A plus the psi B, right? Let me just write down here. The psi A plus the psi B is going to be equal to the 2 of the psi half sum and then cosine half diff. Okay, so let me use this identity or property. Equal to, okay. So now because the amplitudes, right, are just the same, so we can just bring it out from this summation. Then the first thing we're going to have the 2 here times the amplitude A. We have the 2 times the capital A, right? And then times the psi, okay, half sum. It means that we need to sum omega 1t and omega 2t together and divided by the 2. Then we have the omega 1 plus the omega 2 and then over 2, right? And times the t. Okay, so this is for the first term. And then the second term here, right? It's going to be the cosine of the A minus B over 2. So it's just equal to the cosine of the omega 1 minus omega 2 over 2 times t. Okay. Now, let's notice these two terms. Okay, let's notice these two terms. So you can see that these two terms, right, sine and the cosine function, both of them just depending on the times t. Okay, both of them just depending on the times t. But now for the first term here, the frequency should be larger, right? Because we have the omega 1 plus the omega 2 over to the 2, right? So it means that this term we have the higher frequency. And then this term we have the omega 1 minus omega 2 over 2. So it means that the frequency of this term should be lower. Okay, so let me just say it here. Right, so this term, right, we just contribute for the higher frequency. On the other hand, right, it's going to contribute for the lower wavelength. Okay, but then compared to here, this one, okay, so now for this term, it just contributes for the lower frequency. Okay, because I mean because we have the subtraction between the two angular frequency, right? So the frequency should be lower compared to this term, and it means that it's going to have the higher wavelength. Okay, so how it's going to look like, right? So how it's going to look like. Okay, so let's look at this picture. So now for this picture, we have the two waves with the same amplitude, right? In this case, equal to the 10 centimeter. Initial phase are the same because you can see that both of them just overlap at the t at the times equal to the 0. Okay, but then when the times go by, right, the displacement along the x are different. Okay, so in this case, both of them we have the slightly difference in the angular frequency. if we combine these two waves together, we're gonna have the picture which should look like this one. Okay, but one thing that I just want to say is, okay, so let's consider, let's say, the one loop here. Okay, you can see that this, right, it just look like the envelope. Okay, it just look like the envelope for each group here. So what does it mean? So then this envelope, right, because I mean right now the horizontal axis, right, is with the time. So then for this envelope, okay, is gonna contribute for the term with the lower frequency, right? This envelope is just going to contribute for the terms with the lower frequency, which is this term, okay, which is this term. So let me take a note. Let me move it here. Okay, so now this envelope, right, just comes from the lower frequency term. Why? Because I mean, compared to this detail, right, the period here, it should be larger. So then if the period is large, it means that the frequency should be lower. Okay, and now this part, okay, so now this part, so now we just look at this detail. Okay, we just look at this detail. So now this detail, right, will represent the oscillation, right, of the wave, which is coming from the higher frequency. Why the higher frequency? Because the period, right, is smaller. Okay, because the period of this one is smaller, so that's why I just represent the higher frequency, and that's it. Okay, so this type of the picture is just called the beat. Okay, it's called the beat. So if we talking about the sound wave, okay, in the case of the sound wave, maybe you can just YouTube it, right, and then just type the beat of the sound wave, okay, and demonstration. So what you can hear is just something like this. So the sound just play just something like that. Okay, so that's called the beat of the sound wave. So now let's look at these examples. The two identical piano strings, right, of the length equal to the 25 centimeter and are each tuned to the 440 Hz. The tension in one string is increases by 1%. If they're now stuck, what is the beat frequency between the fundamentals of the two strings? Okay. Okay, so what does it mean by the beat frequency here? So it means that we need to find the difference between the two frequency, okay, the one with the frequency equal to the 440 Hz, and the other one is the one which have the tension increased by 1%, right? So it means that the frequency should be different. Okay, so let's find the string one first. Okay, so let's find the string one. Now for the string one, right, we said that the frequency, let's say the F1 equal to the 440 Hz. So this is going to be the standard. Okay, but now for the string 2. Okay, now for the string 2, we said that the tension of this string, right, is increased by the 1%. So it means that the tension of the string 2, right, is going to be the 1.01, the tension of the string 1. So that's what we get. Okay. So how can we just use this information to find the frequency of the string 2? Okay, how can we use this information to find the frequency of the string 2? Actually, yes, we can, because don't forget that both of them, both string, right, are identical. It means that the mu, the linear mass density of both strings, must be the same. Okay, so in this case, I'm going to try to find I'm going to try to write down the speed of the wave. Okay, the speed of the wave in the terms of the tensions and then the mu. For example, this one, the v1, right, is going to be equal to the square root of the tension of the string 1, the ft1, right, and then over the mu. Okay, and then now for the string 2, right, we just do the same thing. Okay, we can just write down the speed of the wave in this on this string, right, the v2 equal to the square root of the ft2 and then over the mu, right, and we know that it's going to be equal to the square root of the 1.01, the ft1, and then over the mu. But we know that the square root of the ft1 over the mu, right, equal to the v1. So then in this case, it's going to be equal to the square root of the 1.01 and then times the v1. So it means that the speed of the string wave, right, in the string 2, it should be square root the 1.01 times of the speed of the wave on the string string 1. So now we're going to try to link this to the frequency. Okay, how again, right? So we said that the v1 equal to the f1 and then times the lambda. The wavelength, both of them should be the same. Okay, should be the same. Now for this one, right, we have the v2 equal to the f2 and then times the lambda. Then if we combine these two, right, so let me just put it to be the red. Okay, if we combine these two, you can see that we have the v2, right, over the v1. No, actually we'll say the f2 over the f1 equal to the v2 and then over the v1. This is what we get. The f2 over the f1 equal to the v2 and then over the v1, right? But now we know that the v2 over the v1 equal to the square root, right? It's just equal to the square root of the 1.01. Okay. Then finally, we can get the frequency on the string 2, right? The f2 is going to be equal to the square root of the 1.01 times the f1 equal to the square root of the 1.01, and the f1 is equal to the 440 Hertz. So, okay, 1.01, right, and then times the 440 Hertz, which is equal to the 442. Okay, then finally we can get the beat frequency, right, which is equal to the absolute value of the 1 minus the f2. Okay, so it's be the difference between these two frequency. So it's gonna contribute for this one, right? For this one, okay, for the high wavelength. So it's gonna be this envelope here. Then we have the absolute value of the 440 and then minus the 442, which is equal to the 2 Hertz. This is the answers.